So what are some more sophisticated structural analytics tasks we can do with a graph? Well, one is to find the diameter of the graph. So this is the longest of all the shortest paths in the graph. So what's the shortest path? Well, given a vertex x and a vertex y, find all the different ways of reaching y from x and take the shortest one of those. That's the shortest path. Now do that again for all possible pairs of vertices in the graphs. The longest of all those shortest paths is the diameter. And so intuitively what this is measuring is, the width of the graph. What's the longest sort of path you have to take to get from one place to another? Okay, and this gives us a measure of how much work we have to do when we're traversing the graph. Okay, so if everything is very tightly connected, then the diameter will be very short. Right, it only takes a few hops to get from anywhere to anywhere. And if the diameter is much longer, then it could potentially take longer than that. So this gives you kind of the 6 degrees of separation, 6 degrees of Kevin Bacon sort of measure. Fine. So what is the diameter of this graph here? Well, we're looking for shortest paths. So let's look at some possible candidates. Well, things like A to F and A to B and D to C are all going to be shortest path 1. So let's look a little closer at ones that appear to be far apart on the page here. So A to C, what's the shortest path there? Well, one path is A to B, B to E, E to G, and G to C, and that's a path of length 4. But there's a shorter one. There's A to B, B to D, and D to C. And so A to C, the shortest path is 3. So let's look at other ones. Well, F to anywhere, well, you can't reach anywhere from F because all the edges point inward. And we're assuming a directed graph for this particular exercise. And G, similarly, you can't get anywhere. You can get to C, but C you can't get anywhere except back to G. So it looks like, starting back from A to G, how many hops does it take to get there? 1, 2, 3. So A to G is 3. And that should be the longest ones. So the diameter of this graph is 3. So we can also measure the connectivity coefficient of a graph as a structural analysis task. So this is the minimum number of vertices you need to remove that will disconnect the graph. And so you can think of this intuitively as a measure of the fragility of the graph, right? How much redundancy is built into it. So if you're designing a network and it turns out the connectivity coefficient of the graph is 1, that means that potentially if one machine goes down, you could partition the network where nobody can communicate. Okay, so if you're an advertiser, you might be interested in the connectivity coefficient of a graph. If you're trying to reach as many people as possible, it could be that if a few people don't pay attention to the ads, then a whole bunch of other people won't send the message if you're sort of in viral advertising or social media advertising. Okay, and so remember in the CAP theorem that we discussed in the NoSQL lectures, P was partitioning, right? So this was if your system becomes partitioned, if your network becomes partitioned, can the systems still function? And so connectivity coefficient could be a measure to help you estimate how likely it is that your network is going to be partitioned. Okay, so what is the connectivity coefficient of this graph? Well, it depends on exactly what we mean by connectivity first. So we can say that two vertices x and y are strongly connected if x is reachable from y and y is reachable from x. Okay, and we might say that they're just connected if x is reachable from y or y is reachable from x. And so this is sort of equivalent to ignoring the directionality of the edges. So if we just assume that everything's undirected, then we'll be using the second definition. So let's assume that for a second. Let's assume we just mean connected here. Well, look, if we don't care about direction of traversing, then if we remove E, is the graph disconnected? No, because you can still reach everything through this other edge up there. And so the only node here that appears to not be redundant here is B. And so if you remove B, though, you'll have two partitions in the network, A and F, and all the other ones here. So the connectivity coefficient of this graph is 1 because we can find a vertex that if we remove it, it'll be a partition network. Okay. And so we already discussed why you might want to compute this. So the connectivity coefficient is a measure of the graph itself and doesn't really give us a way to understand the relative importance of an individual vertex. And so for this purpose, there's been various notions of centrality defined. So one is the closeness centrality of a vertex, which is the average length of all the shortest paths that pass through it. Right? So this, intuitively, you can maybe compare this with the diameter of the graph. Right? If the diameter is long and the average length of all the shortest paths that go through a particular vertex is short, then it's not part of the diameter of the paths that define the diameter of the graph. And so in some sense it's maybe less central or less important. Okay. So another is the between, maybe more common, is the betweenness centrality of a vertex. And this is the fraction of all the shortest paths in the whole graph that pass through this vertex. Right? So if you need to go, all roads lead through Rome, right? If you need to go from Seattle to Atlanta in the US, then perhaps all paths go through one of two different major highways, or maybe one or two cities, the northern route and the southern route or something. And so the betweenness centrality of these two intermediate hubs is high. And so if you think about a public transportation system where all trains lead into some central hub and then go out again, that central hub will have a high betweenness centrality because the shortest path to get from point A to point B always goes through this one central vertex. Okay. So what is the betweenness centrality of vertex E in this case? Well, there's a shortest path A to B to D to C that we found. The shortest path from A to C goes through there. And the shortest path from A to G, A, B, E, G, is 3. So if you sort of add all these up, you'll see that E is only involved in A, B, E, G, and then a bunch of ones that are rooted in E itself, E to C and E to G. So the betweenness centrality of E is 3. Oh, sorry, 3 divided by the total number of shortest paths in the graph. Okay, it's a fraction.